this is a very short topic. Also, there's a lot of information that we've already talked about. So again, sadly, there's only a little bit of information that will be learned. So again, the terms, and some of those terms might look familiar to you. Hopefully they do. If not, pay attention. Content library. Zero math. That is why that the test will be on the device on Friday. All multiple choice, correct. And you may want to have your pre-act table out just so you can reference and not have to flip back and forth. But if you like flipping back and forth, that's fine. The pre-act table, and again, this topic is strictly about the pre-act table. We've talked a lot about the pre-act table already, and so some of this might seem like, remember this in a form of life. Table. The way that the pre-act table is arranged earlier on and currently. Now, some of the things have changed, like this one here, increasing atomic mass. But there was a scientist, Mendeleev, and here it is down here. Mendeleev actually was the first person to think about arranging the elements in a systematic order. And at that time, he arranged them based on their physical and chemical properties, which it is today as well. Arranged based on metallic versus non-metallic, which it is today. And the majority of the elements on the periodic table are what? Metals or non-metals? Metals, very good. We'll show that here in a moment. However, this was the big faux pas that Mendeleev did. He arranged his periodic table based on increasing atomic mass. How is it arranged today? Increasing atomic number. Good, protons. So, yeah, see, you remember. Also, he arranged it based on how elements react with each other. So when we look at the vertical columns, let me pop that up here real quick. So when we look at the vertical columns, all of these elements behave in a similar fashion. All of these elements behave in a similar fashion, and so on and so forth. So when we look at columns, there is a commonality there. However, if we look at, say, the rows or the periods, there's not much similar about those. Blush. Okay, so when we look at periods, really the only thing that we care about, the periods or the rows, is the energy level for the S&P orbitals. So there's not a whole lot that we discuss with the rows, unfortunately. Mendeleev, again, he's given credit for finding out the first, or creating the first periodic table. And he came up with these terms. The horizontal rows are known as periods, so horizontal rows. The vertical columns, he called them families or groups. Okay, so like we already talked about some of those, like group 1A is called what? Alkali metals. Group 2A is, there's your alkali earth, very good. And then we jump all the way over to 7A, and that's halogens, and the last one. And those are the only four you ever need to know. Okay, so we talked about those already, but those are the four that are most common that we deal with. Mendeleev's periodic table was very crude. Be thankful that we don't have that today. But that was his first periodic table. Now, you'll notice, or maybe you didn't notice, or maybe you're able to look at it, he has some question marks for some of these. Like, those are the two that pop out, and here. He knew that those elements existed, they just hadn't been discovered yet. But what was cool about that was, even though he didn't know what it was, what it looked like, he knew what the properties were going to be. He knew how they would behave with other elements. So he was able to predict how those elements that hadn't been discovered were going to behave. Because they didn't know what it was. Where's ER at? This, oh, I don't know about that one. Yeah. Maybe he was theorizing about that and hadn't been named. I don't know who, actually. I know that some of those were named before he was created. Hatched, if you want to say that. Okay, so like, remember the Latin names that we gave him? Actually, we didn't give him any names. What kind of language is what? Oh, that's Russian. I'm sorry. Yeah, that's Russian. He was a Russian. I think it said something up here about Russian chemist here. That's all right, Celeste. You're all right. So Mendeleev, again, not only predicted the missing elements would be discovered, he also predicted the physical and chemical properties for some of those elements. Actually, most of those elements. And then another chemist, and notice that this wasn't too long ago. I mean, just a little over 100 years. The periodic table is the way that it looks now. And actually, my grandfather, which is a pretty long time ago, he graduated from School of Pharmacy in St. Louis back in 20-something. And when I look at his chemistry books, now my chemistry books were about that thick, his were about that thick. So it was still a pretty young science. But the periodic table that we see now, this is pretty much where we're at. And notice that we have these down here, and that's really where they belong, but we don't put that on the piece of paper because it wouldn't fit, and we'd have a lot of blank space. So that's why we don't show the periodic table like this, because you wouldn't be able to read the symbols or the numbers or the information. So we stack it accordingly. But the periodic table, a few of the things that Moseley came along and made the corrections about, it's not increasing mass, it's increasing proton number. Now the columns actually line up pretty well based on their properties. So there were a few discrepancies there. Patterns in the electron configuration. We talked a little bit about this last time. And again, this should be pretty straightforward since we've already talked about electron configurations. For noble gases, when we talk about the outermost S and P orbitals, what's another name for that? We talked about it. Starts with a V. Valence electrons. Those are the electrons that get the dance. Okay, and we'll talk about what a core electron is here in a moment. But valence electrons are the electrons that are important to us because those are the electrons that get the dance. Those are the ones that are involved in chemical reactions. Those are the ones that are involved in forming ions. So when we talk about the outermost S and P orbitals, those are the big time. We don't worry about the d orbital electrons or the f orbital electrons because they don't get the dance for the most part. And especially for this class, it's these, or the valence electrons. And that's what we have here for the chemical bonding. Now, let's separate the difference between valence and core formally. Valence electrons are like my hair. Okay? As gorgeous as it is, I don't care if it gets cut off. I'm going to be okay. I'm going to live another day. And I keep telling my wife whenever she cuts it, go ahead and just shave it off. I don't want it. Okay? It's such a bother. I get up in the morning, wash it, and then dry it, and then I'm done. But if you, and that's what I treat as valence electrons. So they come and go, no problem. Core electrons, I treat as my heart. All right. In other words, once I have my heart in place, I don't want anybody taking it. I'm going to fight to keep my heart in. The valence electrons, take them. It's okay. If you want to put what's it called when you put extra hair in your hair? Extensions. Yeah. So the non-metals are like they're getting extensions, where the metals are losing their hair, so to speak. But core electrons, we'll talk more about core a little bit later on. Yeah. Sorry, my bad. I butchered that. Very bad. All right. Remember that no more than 2 electrons can reside in each orbital. So how many s orbitals per energy level? Very good. Okay, your voice is being picked up on the microphone and everybody yelling that. How many p orbitals can we have per energy level? 3. Very good. Okay, so 1 plus 3 is? Very good. So we can have a maximum of 8 valence electrons, no matter what we're looking at. Keep in mind, d orbital, here, let me pop that up here. D orbital electrons do not count for valence. Okay? These do not count for valence because, again, it's only the outermost or the highest energy level of S and P. Yeah. Are you going to see pictures of all that? Say that again. You get that pictures? You think that this is fake? You think this is fake?
Oh, yeah, that's fake. There's none of that.
It's all witchcraft, remember that. All right. So when we talk about electron configurations for alkaline metals, if I look at alkaline metals, which are which group again? Good. Okay, so group 1A. And when you look on your periodic table, you'll notice there's something kind of wacky about this. Okay? So group 1A is right here. And all of these elements have how many valence electrons? Group 1A has how many valence electrons? 1. Very good. What about these guys over here? How many valence electrons? In group 3A? 3. You picking up on the pattern here? How many valence electrons in group 6A? Wow. What about 5? So always look at the number. So if I were to ask you, let me zap that. If I would say, okay, silicon's right there. How many valence electrons does it have? You could, 2 ways you can do it. You can do it the hard way or the easy way. You can go, okay, well, silicon's in row 3, so I'm going to go 1, 2, 3, 4, or just go right there. There it is. Yeah.
Okay, so are the only ones that have valence electrons the ones with A's next to them?
Beautiful. So if it's not these guys, which are, this is, yeah, I did that right. This is called the representative elements. So if they're not A groups, they're not the ones that we're going to be talking about, the representative elements. Okay, good question. And the reason being, if I were to look at a particular row, say this row right here, okay, the 4th energy level, if I'm looking at that, my outermost, in other words, my 4th energy level, only apply to the S and P's. My D's are a 3rd energy level. So they don't get the dance. Let's get back on track here. So everybody has the blanks here. I think I pretty much said that when looking at the periodic table. So whatever column, if it's an A column, that's how many valence electrons it has. Okay. And again, that all is for the representative elements. Again, if it doesn't have an A at the top, it's not representative. Okay. And you'll notice that there's no column numbers for the F's. Really, we don't need them. I think the reason why they gave the d orbital elements column numbers is just to make people happy, but we really don't do anything with them. All right, so now looking at ions that are formed, and again, we're staying with the representative elements. So, and I'm gonna, are there blanks on there from here to here? Okay, so let me go back to the periodic table and let's talk about the ions. All right, so now in terms of ions, and if you can like zoom in, you might be able to see the charges on there. But when we talk about ions, if I have, say, 3 electrons or less as valence, okay, I'm talking about valence electrons. If I have 3 or less valence electrons, then what's going to happen is it will lose those electrons so that it has no valence electrons. Okay. If I have 5 valence electrons or more, it will gain electrons to get an octet. Turn that off. Okay. To fill the octet. What does fill the octet mean? What does octet mean? 8. Okay. So fill the octet means that we're going to fill up to 8 electrons. So when you hear the term fill the octet, that means that we're going to fill up those orbitals, the S and P orbitals, so that there's 8. Okay. So when we look at 3 or less valence electrons, we're talking about groups 3A and back. And then 5 or more, we're talking about 5A and forward. Okay. Now you may have noticed I didn't think about the forwards. It can swing either way. We'll save that for AP. So like looking at carbon, it can either gain 4 or lose 4. I don't want to trouble you with the most common. But this represents for the most common ion. So if I look at, say, magnesium, how many valence electrons does magnesium have? How many valence electrons? 2. So is it easier to lose 2 or gain 6? Lose 2. So what's magnesium's most common charge? +2, -2. If you lose 2 electrons, you're becoming more positive. Good. So all the elements here have what charge? +2. There you go. That's a periodic trend there. Okay. If, oops, I don't want to erase you. What if I look at, say, phosphorus? Okay. How many valence electrons does phosphorus have? 5. So is it easier to gain or lose electrons? To gain, okay, because it has 5 or more. So how many will it gain to fill the octet? 3. Okay. So what will the charge on phosphorus be? -3. Very good. And I think we talked about that a little bit. I think for the notes I may have accidentally put that in the wrong spot. So let me change that real quick. To fill the octet. Okay. So again, filling the octet means that we're filling up those S&P orbitals. Okay. Let me give you one more. Where shall we go? Iodine. What's the most common charge for iodine? When it's an ion. -1. Very good. Because it has 7 valence electrons. Again, we only care about the p orbital electrons and the s orbital electrons. These don't count. Okay. So since there's 7 valence electrons, then it will gain 1 more electron to have an octet. The blue ones? Yeah, there you go.
Are you talking about these turning into ions?
Changing into ions. And you do that by gaining or losing electrons. Awesome. And you'll notice, and I can't zoom in. I don't think I can zoom in. Yeah, I can't zoom in on here, but those are the numbers or the charges. Most common. And the bolder one,
Why do they have multiple?
we'll talk about that later.
But can you explain like what it would mean to lose or gain or like?
You're not talking here. Don't look in
No,
there.
not
Okay.
Like
Sodium? Okay. All right, now listen. So the question is, we're looking at sodium. How many valence electrons does sodium have right now? 1 valence electron. Okay. So is it easier to gain 7 electrons to fill up the octet or to lose 1 electron? Lose the 1 electron. So it'll lose that 1 electron, and then it'll only have 10 electrons, but the proton number still stays 11. So now it has a +1 charge.
So yeah, if it's 3 or less, it'll just.
Correct. Because it's easier, like if I look at aluminum, let me do one more. So if I'm looking at aluminum, and you might say to yourself, but the journey's so far. No, don't think of it like that. There's only 3 valence electrons, and it wants to, if it loses those 3 electrons, it'll have the same electron configuration as who? It'll be isoelectronic with who? Remember, we talked about isoelectronic last time. Good, neon. So it'll lose those 3 because how many valence electrons does aluminum have? 3. And so if it loses those 3, 1, 2, 3 are gone, and it started with 13, it now has how many total electrons? 10, which is the same number as neon. Okay. So that's how we think about it.
Okay, so if you were to ask a quiz question about this stuff,
Test question, but go ahead, yeah.
how would it be worded?
What is the most common ion for, say, like beryllium? The most common ion deals with this phrase right here. If you have 3 or less valence electrons, it'll lose those electrons. If it has 5 or more, it'll gain to have 8 or an octet. What's that? +2. I like that. Perfect. Okay, everybody good there? And we'll get practice with that, so don't freak out on it. Alrighty. We talked about it. Okay. Yeah. Wasn't as detailed as this conversation. Again, just like on the test, isoelectronic, that's what we were just talking about. Okay. And here again, it's just going through alkali earths. We'll have 2 electrons that it'll lose, so all the alkali earths, or group 2A, would have +2 charge. The halogens, group 7A, has how many valence electrons? 7. So it'll gain 1 more to fill up the octet. And noble gases, they're unreactive because they're full. So very few compounds, not many that we talk about in here, they don't form anything. They're stuck up. Okay? That's what nobility is. Remember that. Okay. All right, the homework. I'll do question number 1 with you, since I'm feeling nice today. Yeah, Jim. State the periodic trend for the periodic table in your own words. What does that mean? Okay, like. So periodic trend deals with how the periodic table is arranged. So when we talked about Mendeleev, when he first created the periodic table, or arranged the periodic table, how did he arrange it? This isn't the answer. This is still us conversing. Go ahead, Celeste. I'm sorry. Okay, so we still do that today, right? Yeah, he did it by atomic mass, but the periodic table is now arranged by. Right, so you can state on there, periodic table is arranged by increasing atomic number. That's one of the things. That's a periodic law there, or trend. So periodic table is arranged by increasing atomic number, or protons. And the second thing is the columns, or the families, the groups that go up and down, those have similar properties, chemical and physical. That's what all that is. So again, periodic table is arranged by increasing atomic number, or protons. And the columns represent for elements that have similar properties or similar characteristics. Okay. You might see some other questions that look very, very familiar. You may have seen them earlier on or similar to it. But I think the rest of these you should be able to answer.